Hey, Wade Hampton Kim students and other students out there in YouTube land. Today we're going to be talking about electronic structure and the periodic table. We're going to get into a little bit about Bohr models, valence electrons, and ions in this unit, all dealing with the behavior and arrangement of electrons in atoms. So to kind of start with the basics here, I'm going to start with something called the Bohr model of the atom. Now, the Bohr model of the atom is a model where electrons orbit the nucleus in energy levels. And the higher the energy level, the farther away from the nucleus you're going to be. So, energy level 1 is here closer to the nucleus, and energy level 2 would be farther away if this gray area is my nucleus. And if you want to start building models, it's important to know that electrons are going to be put into the energy level that's closest to the nucleus first. And each energy level holds a different number of electrons. The first energy level holds up to 2 electrons. That's this first ring in this Bohr model. The second energy level holds up to 8, and the third energy level holds up to 8. Technically, it holds more than that once you get beyond about element number 20, but we'll get into that later. All right, so let's do a couple of Bohr models here just for practice. The first element I want to do is nitrogen. Okay, so if you look at nitrogen on the periodic table, nitrogen on the periodic table is atomic number 7, and it's got a weighted average atomic mass of about 14.01. Okay, now if you remember from our previous lesson, the atomic number tells you the number of protons that are in the atom. And if you want to show that, you could just go in here and say, all right, I've got 7 protons in the nucleus. Remember, protons are in the nucleus. If you want to get the neutrons for the most common isotope, you could subtract the rounded off weighted average atomic mass. So round this to 14 minus 7 would give us 7 neutrons as well. Okay? In a neutral atom, the number of electrons is the same as the protons because the positives and negatives balance out with each other. So we know we're going to have 7 electrons. Now I'm going to represent these electrons just with dots. And I'm going to start, like we just said, with the first energy level. Now the first energy level holds up to 2 electrons. So I'm just going to put 2 dots in this first ring to represent those 2 electrons. All right, so there's my first 2 electrons. How many electrons do I have left? Remember, I've got to use a total of 7. I've already used 2. That means I've got 5 left that I could put in this second shell. Now I know this says the second shell holds up to 8, but I only have 5 left to put in it. So I'm just going to put 5 electrons in that second shell. So 1, 2, 3, 4, and 5. Voila. Some people like to space their electrons out. I like to keep them in pairs so that I can count them easier once I'm done to check myself. 2, 4, 6, 8. Let's do another one. Let's see here. Let's try this time. Let's do chlorine. Now, if you look at chlorine on the periodic table, chlorine is atomic number 17 and has a mass of about 35.4. I'm going to move this up here to get it out of the way. Okay. So if we start looking at the number of protons, neutrons, and electrons based on what we see in the periodic table, again, the atomic number tells us protons, so we'd have 17 protons. You could subtract to get the number of neutrons, so 35 minus 17 would be 18 neutrons. And then we can start putting in our electrons. Now remember, in a neutral atom, the electrons are going to be the same as the protons, and so we know we're going to have 17 dots here. How many go in the first? 2, right? All right, so there's the first 2 out of 17. Okay? And then we want to go to energy level 2. Now remember, energy level 2 can hold up to 8. So we're going to put the next 8 electrons in energy level 2. Okay. I'm still not 17 yet. How many have I used so far? Well, I've used 2 in the first, 8 in the second. I've used a total of 10, which means I've got 7 electrons left over that still need to be put into this model. And now the third energy level holds up to 8, but we're not going to have that many to put in it. We only have 7 left. So I'll go 1, 2, 3, 4, 5, 6, and 7. Okay? Don't put this last electron to fill up that last energy level with 8, because then you'd have 18, which is more than a neutral atom of chlorine would have. Chlorine would only have a total of 17 electrons. Now, disclaimer, Bohr models are not the most current model of the atom. These things, I think, came out in something like 1911, and we've got a more recent model of the atom called the Schrödinger model, or the wave mechanical model of the atom, and we'll be doing that in a little bit of a later lesson. But this is a good place to start with understanding how electrons are arranged in atoms. And there are some similarities between the wave mechanical model of the atom and the Bohr model of the atom in terms of how many electrons are in each energy level and things like that. The Bohr model is also really good for identifying the number of active electrons in an atom. Now, the most active electrons are going to be these electrons on the outside that are involved in most of the chemistry of the atom. When atoms interact chemically with other atoms, it's the electrons that are on the outside that are most important in terms of the behavior of that atom. And so we call those electrons valence electrons. It's a very important term. Valence electrons are defined as electrons that are in the highest energy level. So if I wanted to show valence electrons in the models that I just drew, nitrogen would have these 5 electrons in the highest energy level, be its valence electrons. Chlorine here would have 7 valence electrons. Okay? Now, because valence electrons are really the most important in terms of the chemical behavior of atoms, oftentimes chemists use simplified models of atoms known as Lewis dot structures. Now, in a Lewis dot structure, you really only draw the valence electrons. So, if we compare what we just did, we just drew a model of nitrogen here. It had 5 valence electrons. The Lewis dot model for nitrogen would simply be the symbol N with 5 dots drawn around it. Now, if you don't necessarily want to draw the whole Bohr model to know how many valence electrons you would have, then there's a shortcut for that. You can look at the column numbers. In group 1 on the periodic table, everything has 1 valence electron, or 1 dot. In group 2, everything has 2 dots. Pretty much everything in the middle of the periodic table, or at least most things in the middle of the periodic table, are probably going to have 2 valence electrons. There's some exceptions to that, but that's not super important, at least for right now. When you get over here into the teens for group numbers, group 13 has 3 valence electrons, group 14 has 4, 15 has 5, and so on. So really you can just look at the ones place to tell you how many valence electrons those atoms would have. Okay? There's one atom in the representative elements that doesn't match the number of valence electrons as the other elements in its family. And I bet if you look at this picture, you can find it pretty fast. Which one doesn't match its group numbers? If you said helium, you were right. Okay, helium has 2 valence electrons, while everything else in its family has 8. Okay? All right, now, so far we've been talking about neutrally charged atoms, and neutrally charged atoms have an equal number of protons and electrons. Basically, the positive and the negative charges in the atom are there in equal amounts, and if you were to add up the total positive charge and negative charge, they would add up to 0. If I were talking about a neutral atom of hydrogen, it's got 1 proton and 1 electron, and positive 1 and negative 1 adds up to 0. Neutrally charged atoms don't tend to stay that way for very long, unless you've already got a noble gas or something like that. But neutrally charged atoms can become ions if they gain or lose electrons. If you look at an atom, it kind of makes sense, right? The protons and the neutrons are on the inside, and the electrons are on the outside. So if one atom, rubs up against another atom or reacts with another atom, it's always these electrons on the outside that are changing. These electrons can be given away to another atom, or they could be, this atom might get electrons from another atom. And if that happens and the number of protons in the middle doesn't change, then you're going to end up with an imbalance in the number of positive and negative charges in the atom. So that's going to happen if you form an ion. So an ion is basically just a charged atom. And again, that's going to happen anytime the number of protons do not equal the number of electrons inside the atom. Now, there's a special word for positive ions. We call positive ions cations. Even though this kind of makes me die a little bit, you can remember that pretty easily because this dumb mnemonic device. Remember, cats have paws, and cations are positive. But anyway, there you go. Negatively charged ions are anions. This terminology actually, I think, comes from battery terminology. A positive terminal on a battery is a cathode, and a negative terminal on a battery is known as an anode. Okay. You notice down here in this picture, a negative ion basically just has more negatives than positives, while a positive ion has more positives than negatives. Okay. All right, so you can predict the charge that ions will have after they've gained or lost some electrons, at least for the representative elements, because most elements have a tendency to gain or lose electrons to try to have the same number of electrons as the closest noble gas. Another way to think about this is that they're trying to have a full valence shell. If we go back to the Bohr model, whatever the highest energy level is, if you can get that highest energy level to be completely filled up, then that makes the atom more stable. Now, noble gases already have that. Noble gases have 8 valence electrons, at least most of them, and helium has a full first energy level with 2. So these are the elements that most other elements want to emulate in terms of trying to have the same number of electrons as. So if you were to, pull out an element like oxygen, and want to know what oxygen does to become stable. Oxygen would try to have the same number of electrons as the closest noble gas. The closest noble gas to oxygen is neon. So for oxygen to go from having 8 electrons to having 10, oxygen would have to gain 2 electrons. And after it does that, if you were to look at a model of oxygen, it'd have 8 protons on the outside. If it was neutral, it'd have 8 protons on the inside and 8 electrons on the outside. But if it gains 2, this 8 electrons is going to jump up to 10. And now the negatives are, quote unquote, winning by 2. So if you were to add up the total charge here, the total charge would be a -2. Okay, so this is showing the charge of that ion. Now you can predict the charge for everything in the same family using a similar kind of technique to what we did before, in that everything in the same column is probably going to take the same charge when it becomes an ion, because they all tend to have to gain or lose the same number to get to the closest noble gas. Like, for instance, if you were to look at lithium, lithium is element number 3, the closest noble gas is number 2, it's going to have to lose 1 electron to make a +1 ion. Sodium is element number 11. It's going to also have to lose 1 electron to go down to the closest noble gas, which is 10. And so both of those have +1. In fact, all of these elements in the first group in the periodic table have 1 more electron than the noble gas that's closest to them in atomic numbers. So they all are going to form that +1 charge. Group 2 all forms +2. When you get to group 3, this is pretty much all +3. When you get to group 4, you'll notice this says plus or minus 4. The reason for that has to do with the idea that it's just as easy to gain 4 electrons as it is to lose 4 electrons, and so you might go either way there. For the nitrogen family, now we're actually going to start counting back down in negative numbers. So nitrogen family is -3, oxygen family is -2, and these are -1. The reason we switched to negatives right here is because all of these would have to gain electrons to get to their closest noble gas, whereas these guys are going to have to go down in terms of the number of electrons to get to the previous noble gas's number of electrons. Okay? All right, so a little understanding, check for understanding here, and I'm running out of time, so I'm going to speed this along. If you were to predict the charges of these ions using the column technique, you could say that sodium's +1, sulfur's -2, and aluminum has a charge of +3. If you wanted to know how many protons, neutrons, and electrons would be in each of these, phosphorus would have 15 protons. You could subtract and get 16 neutrons. This means it gained 3. So if it had 15 and gained 3, it would have 18 electrons in that particular model. Okay, that's all we got time for today. You can try these other examples and pause the video and see how you do. All right, till next time.